Well, let me share the screen. Begin with any questions before we start? I really enjoyed reading your journal entries. They were very well thought, and it was really good. So if you keep that up, I think you'll have
I
something. Yeah.
I do have a question about that logistic. Um, there's a submit button in Canvas. So do are you expecting us to, you know, submit the work there rather than just leave it in CoCalc for you to pick up?
It would be easier for me because from Canvas I can use Speed Grader and then grade your journals from within Canvas. It's a little bit easier. All right. Um, so we've been talking about norms and inner products, and these are the axiom for the norms. These are the axiom for the inner product. Intuitively, you need a norm to talk about the magnitude of a vector. Um, and then you need an inner product to talk about orthogonality. Orthogonal. And of course, if you have an inner product, then you also have a norm, as we saw last time. Now, one interesting thing about these axioms is that they are very general. And in particular, they apply just as fine when you are dealing with infinite dimensional spaces. So let me just say a few words about this. But for instance, what's an example of an infinite dimensional space? The continuous functions on 0, 1, right? The space of all continuous functions. Continuous functions. Right, so from calculus, if you think about what is a continuous function, well, it's a graph of a function where you don't lift your pen when you draw the graph, right? That's what continuous means. And so, you know, there could be many such functions, and functions form a vector space because you can add them, you can scalar multiply them. And so you can talk about norms. So for instance, one of the most popular norm is the infinity norm, which takes the max of f of x. So it's perfectly fine to do that. Let me try to some space here. Where's my what's another example? L1, this is slightly harder to define if you haven't seen any measure theory. But think about functions that you can take the integral of, so integrable function. And then the L1 norm here is just going to be the integral of f of x, right? Maybe more famously, L2 of 0, 1 consists of integrable functions, and then the 2 norm is the integral of f squared dx, and then you have to take the square root. Right? And again, in a very parallel fashion, L2 has an inner product. Um, the L2 norm comes from an inner product, and it's just a pairing where you integrate two functions against each other. And you get your 2 norm that way. So now, these are called function spaces. There's also sequence spaces. This is sequences. And these become important when you are dealing, for instance, with Fourier coefficients and things like that. So those are called little L infinity, for instance. This is the set of bounded sequences. 1, 2, infinite sequences such that the terms stay bounded. There's also little L1, same deal, but now you need to sum the series, and little L2, where you sum the square. And of course, there's going to be little LP as well. So the nice thing about these three axioms is that they apply to a very wide range of situations. And these infinite dimensional spaces are going to be mostly the subject of Math 716, right? So the second semester will deal with infinite dimensional spaces. In 715, in this class, we will basically focus on finite dimensional. All right, going to be our main object of study. But you should keep that in mind, right? You should keep in mind that a lot of what we're seeing in Rn can be generalized to function spaces, to sequence spaces, etc. Right? Not everything, but a lot can be generalized, and it's sort of, you know, Rn is the origins of everything, right? So that's where it all started. All right, so let me, for instance, start out by giving you two examples of things that don't generalize, that are special to finite dimensional space. Okay, so the first one, so I guess I could call it special property. So the first one is that inner products on Rn are basically in one-to-one correspondence. So are in one-to-one correspondence with symmetric positive definite matrices. And so I need to recall what those are. So first of all, a matrix A, we usually will denote it as belonging to Rm by n, right? And so it has m rows and n columns, and it will have entries that look like this. So there are m times n real numbers, and that's why we use this notation. It's a little bit of an abusive notation because Rm by n, the way we think about it, is a column vector, right? Things in here would be a column vector where you would put all the entries kind of like this, right? One after the other. In a kind of a flattened array type of situation. But but we'll use this kind of small abusive notation, and we will use this m times n to mean a matrix with m rows and n columns. Questions so far? All right, so a matrix is symmetric if the transpose returns the matrix itself. Remember, the transpose is when you turn every row into a column. It's kind of amazing sometimes, you know, if you think about it. If you turn every row into a column, it's the same as if you turn every column into a row. And that is a little strange. However, if you were to rotate, right, in the plane, this thing, you know, every row would become a column, and every column would become a row. So, and then up to some shifting of rows and columns around, it kind of makes sense. But now, if you're symmetric, then the transpose is equal to itself. So what does this imply for the dimensions of the matrix?
Not square.
It should be a square, right? So in particular, A needs to be n by n. Because of course, when you transpose, you're going to switch the m and the n. All right. What about positive definite? A is positive definite. This is a property about the quadratic form associated with A. So The quadratic form is an expression right. Usually when you have a matrix, you can think of it as a linear operator, right? That takes a vector in Rn, right? The number of columns, and multiplies it from the left and spits out a vector in Rm, right? So that's the standard way to think about matrices as linear operators. And we will use that point of view a lot. But another point of view is to think of the quadratic form. You can have x on both sides, or you can even have x and y, right? You can have two variables. So the quadratic form actually will involve two variables. And to be positive definite, you need to assume that this is actually strictly positive for every vector x in Rn, which is not the zero vector. Of course, if you put in 0 here, you're going to get 0. But as soon as you are non-zero, you should get a strictly positive result. All right, so that's what symmetric and positive definite matrices are. And the claim, which is a lemma in the text, is that inner products are in one-to-one correspondence with such matrices. So let's state it like this. On one hand, if you're given an inner product, like this, on our end, then there exists a matrix A, symmetric, positive definite. I'm abbreviating here. Some people use SPD. So that the inner product of two vectors is equal to y transpose AX. Okay. And conversely, if you know, if A is symmetric positive definite, well then if you define the inner product as y transpose AX, then this is so it goes, you know, it goes both ways. Now, let's maybe start with the, so let's call this say A and this B. So B, all you need to do is check the axioms, right? Right, and so let's go look at the axiom for a second. Well, symmetry, right? Linearity, and then non-negative and 0 if and only if x is 0. Right, so number 4 is exactly the positive definite property. And number 1 is exactly the symmetry property. And 2 and 3 are the linearity. So it's really simple to verify these things. Now, you might want to check a little more carefully that, for instance, the symmetry, right? That this is the same as this. How would you do that? How would you check that you can switch x and y here?
Multiply it out element-wise, and then use regular multiplication commutativity to undo it.
All right, so method 1. Who was talking?
Brett was talking.
Brett, okay. So Brett is saying, just write it in sigma notation, right? Something like this, ij, yi, a, ij, xj. And then use the property of the any order property for multiplication. You can move this around. I. And then because the matrix is symmetric, you can switch I and J there. And then I and J are just dummy variables. You can call them whatever you want. So you can also interchange them. And now you found that this. Is that what you were thinking?
Yes, exactly.
Sure. Another way, anybody, another way? A little more kind of abstracty thing, right? So this is a number, right? It's a scalar. So you can think of it as a 1-by-1 matrix, right? In particular, a 1-by-1 matrix is equal to its transpose, right? Because you're switching rows and columns in a 1-by-1 matrix, you're not doing anything. But now you can use the property of transposes. And do you remember what the properties are?
You distribute the transpose to each element, and then you switch the order of everything.
You switch the order of everything. So we need to distribute X transpose, A transpose, Y transpose, transpose, right? But now A transpose, because A is symmetric, that's just going to be A. And Y transpose, transpose, that's just going to be Y. That's an alternative way of doing this. All right. So we did show one direction That's B. What about A? If you're given an inner product, then there is a symmetric positive definite matrix A such that that happens. So how would you show that? Well, you need to you have to come up with a matrix, right? So the way to think of a matrix is through the entries of the matrix, right? And there are several ways of thinking of a matrix. You can think of it as a collection of columns. And in that situation, the columns are what happens when you apply A to the standard basis vectors, right? You can think of it that way. Or you can think of it in terms of rows. And that's what happens when you apply the standard basic vectors from the left. Do you remember that from matrix theory?
Mhm.
Everybody okay with it? All right, so, but what about the actual entries? So Aij, the ith entry, well, it's the, you know, it's the ith row and it's the jth column, right? So it's the quadratic form applied to the standard basis vector. So here, E1, En are, the usual 1, 0, 0, 0, 0, 0, 1. Standard. All right. Everybody okay with that?
Yes.
All right. So all we need to do is we need to define Aij to be the inner product of Ei and Ej. And then by linearity, of both sides, you will get that y transpose ax is equal to, right? Because you can write y as the sum of yi's and x as the sum of xj, ej's. And then when you put those in here, you can undo everything and pull everything out. And then, recover the same thing that you would get from here, from this side. All right, so just by linearity, they're going to be the same thing. All right, questions? Good. All right, so, and what is another special property of Rn? What did I call the first property? The name? The claim. Oh, 1. Okay, so 2. And this is a very important fact about norms in Rn, that all norms in Rn are equivalent. That's very special to Rn. In infinite dimensional spaces, this is not the case. So what do we mean by equivalent? Suppose you have two norms. Let me call it, suppose you have norm A and norm B. We're going to say that they are equivalent if you can find two constants, C1, C2. These are universal constants, and they should be certainly not 0 and not infinity, somewhere in between. And I guess you want probably something like that. With the property, they are equivalent if there exists one such that the norm of a vector in the A norm is controlled by the norm of a vector in the B norm, and will control the norm of a vector. This should be true for every vector x. Okay, so that's what equivalent means. Basically, up to a multiplicative factor, maybe like a factor of 2 or a factor of 10, these magnitudes are roughly the same. All right, so there is an exercise in the book that I think I'm going to assign for next week, where you're asked to come up to compute the best constants possible here when the A norm and the B norms are P norms of some sort. Right? So those can be computed exactly, sort of the best constants. Of course, once there is a constant, you can always make it bigger. So, and here C1, you can always make it smaller. So in general, if two norms are equivalent, there are optimal constants above and below, right, that kind of make this as tight as possible. Now, they might not be tight on the same vectors, right? So maybe C2 is optimal for certain vector x, and then C1 is optimal for some other vector x. So little details like that, but something to keep in mind. All right, so how do we prove this? Well, being equivalent is a kind of a transitive property. So if A is equivalent to B and B is equivalent to C, then A is equivalent to C, right? So there's kind of there's a transitive property here. So by transitivity, it's enough to show that every norm in Rn is equivalent to the one norm. Every norm is equivalent to the one norm, for instance, but this is one way to do it. All right, so let's try that, right? So if I have a vector x, I can always decompose it into the standard basis, right? So this is why I kind of like the other notation as a function, because it makes a little bit more explicit the difference here between xi and ei, right? Xi is a number, it's a scalar. Ei is a vector. So if you write it like this, maybe it's a little bit clearer. Right? So you know, if you have a vector with x1, xn, you can always write it as x1 times 1, 0, 0, 0 plus xn. So that's the first observation. But now, what do we know about this norm here? What properties can we assume about this norm? If I tell you I have a norm, what properties can you assume for it?
We know it's positive. We know it's only 0 if all the components are 0.
Right. So the axioms, right? That's all we can go by. So it's the axioms. And in particular, we can use the triangle inequality. That's pretty much our only tool. Right? So by the triangle inequality, the norm of x is less. I can pass the norm inside the sum. And then by homogeneity, I can get the xi's out and get that estimate. Right? But Rn, the dimension of Rn is fixed. It's capital N. We are not moving that. So I have a finite number of magnitudes here. I can estimate them by their maximum, right? And then it will come out, right? So this is less than the maximum norm when I goes from 1 to n times the sum of the xi. So but now the sum of the xi, this is the one norm. So we get max ei times the one norm of F. That makes sense?
Mhm.
So we found one direction, right? We found, what did we call it? C1 or C2? C2, I guess. Doesn't really matter, but C2. I'm trying to prove that this norm that I'm given is equivalent to the one norm. What about the other direction? The other direction is a little bit harder. So let's introduce the unit sphere S of vectors that have one norm equal to 1. Right, and we remember from a few lectures ago that S kind of looks like that, right? At least in R2, in higher dimension is a little more complicated, but it's some kind of prism. But in any case, the function F equal norm X. This is a function from vectors in Rn to numbers, right? It's a multivariable function, but it's going to be continuous. With respect to S equipped with the one norm. And well, this is, you know, something that needs to be proven, but essentially will follow from what we've shown up here, right? Because if you have, you know, let's use this estimate up here, right? It's saying that if we apply that estimate to the difference of two vectors, then it looks like that. If you know a little bit of analysis, this is telling you that F is a Lipschitz function, right? So if you don't know this term, it's not important. So what's important is that, as for instance, y tends to x, right? In the one norm, then that it will imply that it will, you know, say if this goes to 0 in the one norm, then this goes to 0 in the other norm. That's what I mean by continuous. And the other thing is that because of the finite dimensionality of Rn, this prism here is a compact set. So we need a little bit of analysis here. If you haven't seen that, it's not super important. So S is compact set in Rn. And if you have a continuous function on a compact set, then it will attain a minimum. So attains its minimum All right, questions so far? Good. We're basically done now because we can say that norm x um, so let me say for x in S, norm x is greater than the minimum um, you know, the value of the function at x is greater than the minimum of the function over the whole sphere, unit sphere. And let's call this C1. And because f attains its minimum, then it has to be strictly positive. Right? Otherwise, if the minimum was attained and was 0, then the vector would be 0. But that's a contradiction. It would not be in S anymore. All right, so we have a strictly positive number here, C1. And we can say then that norm x is always greater than C1 times the 1 norm because we are on S. On S, the 1 norm is 1. In general, what you're going to do is you're going to normalize, you're going to divide x by its 1 norm, take the, the new norm of it, that will come out. So this is going to be greater than C1 because this is in S. And then by homogeneity, this comes out. And then you solve. In general, for general non-zero vectors, we get this lower bound here in terms of the 1 norm. All right, so it was really important, this compactness of a set in a range. So the finite dimensionality is very important. When you go to the infinite dimensional spaces, you lose the compactness. Now, there are many ways of recovering certain forms of compactness, some sort of weaker forms of compactness, but those are not enough to guarantee this, this property for the norm. So being compact in the norm topology, for those who know what I'm talking about, it's a property of finite dimensional space. All right, questions? And also, I've just noticed that we are at the 12:20 minute mark, so we are out of time. But any questions? I can take a few minutes here. So on Wednesday, if you have questions about the homework, let me know. We can spend a few minutes talking about that. And then I thought that before we launch into matrix norms, I thought I would do a little bit of a review of matrix theory, and especially the topics that are usually skipped that are kind of on the edge at the end of matrix theory that sometimes are covered and sometimes are not covered. And those are actually exactly the topics that we'll need. So I'll do a little bit of a detour on Wednesday and Friday into just basic matrix theory concepts. And even if maybe I don't prove everything, and we will prove it later in the semester, but at least you know what we're dealing with, you know what we're talking about. All right, other questions?
Which aspects of the theory are you referring to there, sir?
Sorry?
You said that. Oh, which aspects of the theory were you referring to that you were referring to that they may or may not be covered typically?
Well, so like the whole business about diagonalization of matrices and diagonalization of symmetric matrices, the singular value decomposition, and things like that.
Gotcha.
Yeah. I don't know how
Well,
much
thank you.
they've been covered in matrix theory, but
I had 551 this summer, and so we covered diagonalization and singular values. And if there was one particular technique that got, well, I get would be singular value decomposition. I seemed like we went through real quickly, but we went through it thorough enough, I would say. We just didn't do anything with it.
okay, but it's good to refresh, right? To kind of
Yeah, no, definitely.
see
I
it
find
from
that
a little.
at this stage of my life, I find that I need constant reinforcement, just to build proficiency.
Yeah, yeah. I think that's what it is. You know, that's what learning is about. Hearing the same thing from different sources in different ways. So, all right. I'll see you on Wednesday.
Cool. Thanks.